Okay, so here I've got a moment of inertia for a disk. This can, it of course depends on the axis, but I'm just going to run through a couple the more typical axes. So if we just consider an axis which goes to the center and is perpendicular to the disk, then our moment of inertia is, for a continuous object, is going to be the integral of r squared dm. And the trick is always to identify this dm. And so if we consider a small area of mass at some r away, and some thickness dr, we can extend this out. And so this length would be 2 pi r because it's a circle. And its thickness is dr, giving it an area, or a small unit of area, of just 2 pi r dr. Right, so this is a line segment, or we're considering it, I guess, as a rectangle, so you just multiply the width times the height. Now, to get from an area to a mass, we have to use the density, or the area density anyway. So this would translate then to some small amount of mass by multiplying by the density, where for the full disk, we must have that the mass, I'm going to use capital M just to differentiate. We must have that the mass is the density times the area, which for a disk is the density times pi r squared, where r here is the full radius. Again, just to, that shouldn't be an equals there. Again, I'm just going to use capital R to differentiate from the lowercase r, which I'm using for the small segments. Okay, so if that's our area segment, then now we can say that our moment of inertia is integral r squared times rho 2 pi r dr, which is rho times 2 pi integral r cubed dr from 0 to r, as we're integrating from 0 out to the full radius. And so we have 2 pi rho. The integral of a power is you just pop the power up by 1 and then divide, so it'll be r to the 4th over 4. And our limits are 0 to r. And now when r equals 0, we can see that this is going to be 0, so we just need the upper limit. So then 2 pi rho r to the 4th over 4. And so we can cancel this 2, but we can also notice that we just defined our mass as rho pi r squared. And so that's in here. So we can take out the pi, the rho, and r squared to give us m r squared over 2. And so there's our moment of inertia for an axis which passes through the center of the disk and is perpendicular to the disk. Now I'm just going to expand this by also doing for an axis which passes through the center but lies in the plane of the disk. So again, it'll be the integral of r squared dm, but now our mass segments are a little trickier. So if we wanted to identify one, it would be, and remember the r's are always perpendicular distances. So these would be our r's. And here's one such segment where it would have all the same r from the axis. So I'm just going to expand it a bit. Okay, and we're just looking at this half of the circle right now. Right, so these would all be the same r's. And now it's handy to move to a theta system. So that would be theta in there. The reason I say this is because now we can define, and you'll notice that this is the radius of the circle, right? And so this side is r cos theta, and this side over here is r sine theta, and that equals our r, right? So our r value is r sine theta, and this length here is our cos theta, meaning that the entire length is 2r cos theta. So that's our little mass segment, and if it has a width of dr, then our tiny area segment this time is 2r cos theta dr. Now we want to move to a theta system, and so the easiest way to do that is going to be to just use integrals. So if r is r sine theta, then dr is r cos theta d theta. Plugging that in for our dr, then our area segment is now 2r squared cos squared theta d theta. And again, similar to above, we can now define a small amount of mass as rho 2r squared cos squared theta d theta. Now plugging in these values for our mode of inertia expression, right, so now r squared, so integral of r sine theta squared, and then our dm, which is now rho 2r squared cos squared theta d theta. And now our integration limits. So the way I defined everything is we only need to move from 0 to pi over 2, because that'll cover the whole half circle, but then that's only half of the object, so we need to double it. So it would be double 0 to pi over 2. Okay, so now collecting some of these constants out front. So I've got a rho r squared and another r squared. These are all the full radius of the circle, so that would be 4 rho r to the 4th integral 0 to pi over 2 sine squared theta cos squared theta d theta. Okay, so now for this integral, I had to look it up. So then our mode of inertia is 4 rho r to the 4th. And so the indefinite integral is 1 over 32 times 4 theta minus sine of 4 theta from 0 to pi over 2. So now plugging in our limits, 4 rho r to the 4th, 1 over 32, 4 times pi over 2 minus sine of 4 times pi over 2 minus 1 over 32 times 4 times 0 minus sine of 4 times 0. So obviously that's 0, that's 0, so this whole term is 0, and that's sine of 4 pi over 2, which is the sine of 2 pi, which is 0. So pretty much everything goes to 0 except the first term. So then we've got 4 rho r to the 4th times, so just moving some stuff around in here, 2 pi over 16, which is equal to pi rho r to the 4th over, so 2 times 4 is 8, 8 over 16 is 2, which means I messed something up. What did I do here? 4. So that should be 2. Oh, oops, there should be a 2. Should be a 2 here. There we go, that's what I messed up. So that should just be pi over 16. There we go, and then that should be pi, that should be over 4. Okay, there. And then our full mass is defined as rho pi r squared. So then now our mode of inertia is mr squared over 4. Alright. So that's for an axis which passes through the center of the disk and is in the plane of the disk. And this is for the mode of inertia which lies about an axis which is perpendicular to the disk and passes through the center. And as I showed in a previous question, we can move to pretty much any other axis that's perpendicular to these ones fairly readily. Okay, so just running through the solution here. So we've got our mass, our density, our radius. So here's so this is just for the axis perpendicular to the disk, which is fine. As this question just asks moment of inertia for a disk, so it doesn't define any axis system. So I'd say this looks good. I've just expanded upon it a little bit, and there's obviously other axis systems which would be possible.